Hello again. This is again a video on Calculus 1, Chapter 3. Okay, so let's get started. I hope you're doing well. We are going to talk about derivative, but this time we are going to use that idea of limit that we learned in Chapter 2 to define derivative. Okay, so let's do that. So in calculus, of course, has so many applications in different fields. It's kind of hard to talk about all of them and name all of them, but in any field that you can think of, there are variables that change with respect to some other variables. And whenever we have a situation where we have values of variables changing with respect to some other variables, then calculus is a really good tool to use. Of course, you still need linear algebra to take the points in space and convert them to numbers. And then you need differential equations to solve the equations that we get as a result of application of calculus. All of that you're going to learn in your career, of course, depending on what kind of engineering or what kind of major you're getting into. So let's get started on this. The first thing I want to do is I want to show you a timeline. Recently, people analyzed the historical evidence and then realized that there was actually calculus before it was discovered or rediscovered or invented in Europe. So you see the timeline in India, in south of India, a school called Kerala School of Astronomy and Mathematics. And there were a number of mathematicians, and you see the names of them over here. And the timeline goes from like 1300s, 1400s to 1500, 1600. But the timeline in Europe starts with Descartes, with the coordinate planes and the coordinates plane and rectangular coordinate plane, Cartesian coordinate plane, and then the rest of the mathematicians, Cavalieri, Fermat, Wallace, Barrow, Gregory, Newton, Leibniz. And the calculus that we are learning here is about the calculus of this time, but of course there was calculus here. And in calculus 2, we're going to look at some of the calculus that was done actually in Kerala School of Astronomy and Mathematics in India. And that was coming up with infinite series for sine and cosine functions and things like that. So just wanted to mention that there are people who actually give credit for invention of calculus to Kerala School of Astronomy and Mathematics in India. Okay, so now in chapter 2 we talked about the idea of secant line, which is basically a line that connects 2 points on a graph, and the idea of tangent line. There are two ways to name these 2 points. One way is to start with a point A. So we are interested in knowing what is the rate of this function at this point. For example, this function is increasing, so we like to know the rate of increase of this function at this point, point A. And to find that, we said in chapter 2, we're going to put a point close to it, either to the right of it, to the left of it, doesn't matter. But let's say to the right of it. And then we assume the second point to have an x coordinate, we call it x. And then the y coordinates, of course, would be f of x and f of a. So the slope of this secant line right here is given by this expression. And then we can also name them this way. We can call the first one a and the second one a plus h. And then this would be the expression for that, because the slope of the secant line would be this minus this, right? F of a plus h minus f of a over a plus h minus a, which is h. We could also call this x plus h and x here. Later we're going to do that. So we can actually call this x and x plus h, and then we have expression with x here. All right. So let's that is a famous expression, this one or this one, or with the one, the one with x, and this is called difference quotient. And you learned that probably in algebra, and in algebra you just created these difference quotient for different functions, and you probably didn't know why you were learning it. Now you know. So let me take you to this animation here online to show you what we want to do in this section. So what we want to do in this section is this. You see, this is the secant line, and this right here, the red one, is the tangent line. So what we are interested in doing is this. We are interested in taking this point and making it closer and closer to the point at which we are interested in figuring out the rate of the function, right? Now, we don't want this point to be exactly this point, because that's not what we want. And the reason we don't want that is because that would cause the denominator of the difference quotient to go to 0. And we don't want that. So, so the way we are going to do this is by using the idea of limit. All right, so that's the idea. So the idea is that if I want to find the slope of the tangent line, which is the red one, all I have to do is basically have this point approach the other point. And how do we do that? Well, we're going to have to move let the x coordinate approach the x coordinate of this point, right? So if you call this a and call this x, then you let x approach a. If you call this a and you call the other one a plus h, then we're going to let h go to 0 so that this point would approach the other point, like that. Okay, so that's the idea. So the idea is that we can get really, really, really close to this point. Not exactly the point. Remember, we cannot get to the point. Even though it looks like we are getting to the point, that's just the trick that the computer uses to graph the tangent line. We are not really at that point, right? So because really this graph is not all filled. If you zoom in, you see it has got pixels, right? And since we can't really recognize the spaces between the pixels, we see a solid line. It's not really solid, right? And the background is full of holes, right? But that's the idea. So let me close this and go back to where we were. So, so here's the idea. And this idea was controversial because, you see, we said that we want to get closer and closer to this point, right? So here's the point, here's another point. And what we want to do, we want to, move this closer and closer to this point. But how close? Because we can't be exactly this point, because that would make the denominator go to 0, right? So you see, if I call this a and call this a plus h, and let h go to 0, h cannot be 0, because if h is 0, then this point becomes this point, and the denominator, remember, is h. So the denominator is going to go to 0, so we're not going to have the slope, right? So you can't find the slope if h is 0. So what we have here is that h has to be small, but how small can it be? Now, before the idea of limit, mathematicians used something called infinitesimal. See, infinitesimal. Infinitesimal means infinitely small, basically. And they assume that infinitesimal is so small, that means h, which of course later we could call it delta x and then dx. So we're going to get to a point where we are so close to A that we can't even measure how close we are. That's the idea. It's so small that we can't even measure it. Well, that idea didn't really make much sense to some people. This guy, Berkeley, criticized and made fun of mathematicians because his question was to mathematician. He was a priest, so his question was, well, what is this number you're talking about, this dx number? What is it? Well, the mathematicians said that it was a number really, really, really small, close to zero, but not zero. And then when he asked, what is this number? They said, well, it's a number that is approaching zero, but is not zero. So Berkeley made fun of them and called the number ghosts of departed quantities. That means this number is approaching zero. So it used to be a number, but is dead now. That number is dead, departed, right? And then now we got the ghost of that number that was before it. So that's kind of made fun of this idea. So limit came along, and the limit got rid of that confusion and kind of limit answers actually Mr. Berkeley. So the idea of limit can answer this, and we're going to see how. Okay, so let's look at how this was done before the invention of limit. So what is the slope of the tangent line at x for this function? So suppose we have a function, so here's a function. We want to know what is the slope of the tangent line at x. Now, tangent line basically, as you saw in that animation, basically what we're going to find out is that what happens if we actually tangent at that point, what would be the slope of that tangent, and the slope of that tangent line is the rate at that point. But the question was, how do you tangent to this, right? And the way you do tangent to that is you put another point here, you draw that line and let this point approach this point so close that this line, the secant line, is almost the tangent line. Again, that's the idea of infinitesimal. So that infinitesimal, let's call it dx. So we're going to go to the right of this point, not that far, but we're going to go to x plus dx. So dx is a really, really small number, which is the infinitesimal. So this is how they did it. They said, okay, why don't we substitute dx in here and see what happens. Now here we have x to the third, so you have to know how to expand a plus b to the third power. If you don't, you can review it. You're going to stop the video and review a plus b to the third, the formula. That's the formula. And if you know it already, that's good. That's how you expand x plus a plus something, a plus b to the third. Okay, so we expand this. We need this because we have to substitute dx for x here, right? We have to put dx here, we have to put dx here, right? And then, so we have to put x plus dx here. Sorry, I missed the x. X plus dx here and x plus dx here, right? That's the y value for this point. So let's do that. So what is f of x plus dx? So we have to put x plus dx here, put it here, and then see what we get. If you put it here, we have to expand it, so we get all this, right? So this part right here, all the way to here, is basically this if you put x plus dx for x, right? And this part is this if you put x plus dx for x, right? That part. So this will be f of x plus dx, right? So that, remember, that would be our numerator, right? So we need f of x plus dx minus f of x divided by dx, right? So remember, dx plays the role of h here, right? Okay, now, if we do that, what is f of x plus dh is that? Now what is f of x? F of x is basically this whole thing, right? This is f of x. So in the numerator we have all of this and then minus that. But here is the argument. So what they did, they argued that this thing right here, if we assume that dx is really, really small that you can't even measure, then dx squared would be even smaller. Remember, if you have a small fraction, let's say 1 over 5, let's say 1 over 10, if you multiply it by 1 over 10, you get 1 over 100. So it becomes even smaller, right? So if you raise a very small number to the second power, it becomes even smaller. What if you raise it to the third power? That becomes even smaller, right? Let's say you have 1/10 and you multiply it by, you write it 3 times multiply, that's 1 over 1,000. That's much smaller than 1/10. So they argued that we can just ignore what? We can ignore these, right? We don't ignore dx itself, but we ignore these, right? So we ignore this. If we ignore these, then the numerator becomes what? Becomes this part without this, minus f of x, which is basically that, right? So f of x plus dx minus f of x becomes basically this right here, if you simplify it, right? So you see, if you take this minus that, and you ignore these, and then apply the minus here, right? You get minus x to the third minus 2x. So this would be all of these without that. So this is ignored. So all of these and that's the numerator, right? So that becomes our numerator, right? Which is given right here. So that is our numerator, which another name for this is really, another name for this fraction is like delta y over delta x. Delta means change, so change in y values and change in x values. X goes from x to x plus dx, so change in x values is dx, so that's delta x. So delta x and dx are basically the same. But delta y, according to this argument, delta y is not the same as dy. So delta y would be if you take this whole thing and subtract that from it, that's our delta y. But they argued that we're going to ignore this part of it, and now we can call this what? We can call this dy. And dy is just the numerator when we, simplify it according to this argument. So that's our numerator, right? And if you look at this, you see that this gets canceled, right? This gets canceled. So what you have left with is basically that. That's the numerator right here. So our numerator becomes basically 3x squared plus 2 and then times dx, right? And the denominator is dx. So dx goes away with dx, right? I mean, no, I did that. So the numerator becomes, yes, so dx, right, dy. So what they said was dy, let me rewrite it here. Dy dx is going to be that divided by dx, which the mathematicians in Europe basically said, like Newton and Leibniz and others, the argument was that this now gives us what? There is no limit at that time. So they're not going to say let dx go to 0. There was no limit at that time. So what they said was that if we assume that dx is really, really, really small, and then we do this cancellation, we end up with what? We end up with the slope of the tangent line at that point. So whatever that point is, let's say this point is 2, then we're going to put 2 here. 3 times 2 squared plus 2 would be the slope of the tangent line. Let's say x is 1. So if x is 1, the slope of the tangent line is 5. That means the rate of this function at x equals to 1 is 5 units per 1 unit of change in x. So that was the way that calculus, the differentiation part of calculus was done without the idea of limit. Okay? All right, so again, this is the explanation of what is going on here. You see, here is the point that is really close to this, right? So if we were to use delta y over delta x, that would be the slope of the secant line, which is this red line right here. Right, let me kind of draw it. So it would be a slope of that line, right? So that's the slope of that line. But this is the slope of this line. And since we assume that dx is really, really, really small, then that dy and delta y are really close. So what's the difference between them? You see, from here to here is delta y, right? And from here to here is dy. Because what's the slope of the tangent line? Is y, right, over rise over run, right? If you go from this point, let's say, to this point, the slope is going to be what? Is going to be dy over dx, right? And dy here, my notation, I have to fix that. Delta y and my delta y and delta and dy are not correct, so let me fix it. So dy would be this right here. I got too excited about that. And dy is actually this right here. Okay? Let me fix that. I'm going to fix it in the notes as well. Okay, so this is delta y between the difference between y values from here to here, and that's the dy. Okay, so that's the idea. All right, so so to define the derivative, we're going to use the limit. We're not going to use that idea of infinitesimal. We're going to use the limit. How? Well, we're going to take the limit of the slope of the secant line when, again, this point approaches this point. How can we make this point approach this point? We let x approach a, right? If we name it this way. If we name the first point a and x, then we let x approach a. If we use the other one, if we use this naming, if we put the first point, make the first point a, and make the second one a plus h, then we let h go to 0, right? So there are two different ways to do that. Sometimes this is more convenient to use. In some functions, the other one is more convenient to use. All right, so that's the idea. Now, we're going to name that the slope of the tangent line at a given point. We're going to call it f prime of a. Now, f, of course, is a function notation, and we're going to see that the derivative of a function is actually a function itself. So derivative is a function that gives you the slope values at any given point in the domain of the function, right? If it's differentiable. I'm going to talk about that. Okay, so the notation is f prime of a. So f prime of a is the slope of the tangent line at a to the graph of the function. And that is limit of f of x minus f of a over x minus a when x approaches a, or the other notation, right? Which is f prime at x. Again, I have to fix that. This is f prime at a. It would be at x if we change this a to x, right? If I change this to x, that would be f prime at x. But if it's a, this is a, okay? All right. So if this limit exists, of course, then we say that the slope of the tangent line is f prime at that number. All right, so find the equation of the tangent line tangent to the graph of x equals to f of x equals to x squared at x equal to 3. So what we have to do, we have to set up that limit, right? Let's use this notation. So in this case, our a, right, equals to 3, and we're going to use this setup. So we're going to take the limit of f of a plus h, a is 3 plus h minus f of 3 over h when h goes to 0. So we have to take this limit, and we did the whole chapter on limits, and we know this limit, something is built into it. Notice, so a problem is built into this, a trouble is built into it, and that trouble is, in chapter 2, was when we got 0 over 0. So in this chapter, we always get this. So the trouble is built into this, and you see why, right? If you let h go to 0 here, what do you get? You get f of 3 minus f of 3 over h, which is 0 over 0, right? We always get that. So that means we always have to find a way to get rid of this h in the denominator. So let's do that. So when we set it up, we know we're not going to be able to find this limit by substitution. The trouble is built into it. So what we have to do, we have to use our skills in chapter 2 to get rid of that h. How do we do that? Well, in this case, you just simplify it and you get it. See that? You can easily get it. So 9 and 9 cancel here, right? So we can factor one h out and then get rid of the h. And now we get limit of 6 plus h when h goes to 0 is just 6. So this right here is the slope of the tangent line, right? So slope of the tangent line. Another name for that, of course, is f prime at 3, right? And the way we write the equation of the tangent line is, now in algebra, you know that y minus y1 equals to m times x minus x1. That's the equation of a line that goes through a point, x1, y1, and has a slope of m, right? So in calculus, we use the same thing, except x1 and y1 are actually a and f of a, right? And our m is actually f prime of a, right? So the way we write it is y minus f of a equals to f prime of a and times x minus a, right? So instead of using this, we're going to use what? We're going to use this idea here, because that's more calculus-like, right? So now, to write the equation of this line, tangent to this graph at this point, we're going to write y minus f of 3 equals to f prime at a, which is the slope of the tangent, times x minus 3. So in this case, what is f at 3? If you substitute here for 3 squared is 9. So that's f of 3, right here. So it would be y minus 9 equals to, what's f prime at a? Well, we found it here. So we put 6 for that. And then what is a is 3. That's it. That's good enough. If you have to simplify it, you can write it in the form of mx plus b. But that is the equation of the line tangent to that graph. Okay. Now, of course, we can use technology. You can use a calculator or this GeoGebra again, very useful. Let me see. So with this, we can just go to, we can just put f of x equals to x squared, right there, and then we can put a point on this graph. Oops, this is the wrong place. I want to put a point on object. So this is my object. So I put a point on it. And I don't know why I can. There you go. Okay, and then I'm going to graph a tangent to it. There you go. So let's go graph a tangent. There you go. And that point right there. Now if I move that point, you see that's the tangent to this graph, and we found the tangent at 3, which is way over there. So I have to zoom out a little bit to get this. So here is 3, it's about right there somewhere, right? See, right about there. That's at 3. I have to expand this so I can see 3 on the x-axis. Move it. Oops. There you go. There. So that's what we found. We found an equation for this, and GeoGebra gives you the equation for it. Of course, it's not exactly right now because I'm not exactly at 3. I can move it at 3 maybe. Right there. That's at 3. How do I know? Because I got the same what? I got the same equation, see? Okay? Now you can also do this with a calculator. Let me close this so it doesn't use memory. And I can do it with a calculator. Now, I don't want you to do it with the calculator from this chapter. I want you to work by hand and do a bunch of these by hand. Calculators should be used for more involved problem, more difficult problems, and also to kind of check your answer. So here's x squared, and we can graph it maybe in zoom 6. And then we can go over here and then go to actually draw right here. We go to graph and then go to draw. And then you see tangent right there. Draw a tangent, and at what point do you want to graph a tangent? Just put 3 and enter. And it graphs a tangent line for you at 3 and gives you the equation for it. See that? All right? So we can use technology to do the problem, but I want you to do it by hand at this point. Okay, so here is the limit. If we decide to use the other structure instead of a plus h minus f of a over h, you can use f of x minus f of a, x minus a, right? When a here is what? Is 3. So we have to do x squared, right? X squared, which is f of x, minus f of a, which is 9, right? Divided by x minus 3. And notice that in this one is a little bit harder to get the answer, because with this structure we got the answer just by simplifying it, but here you have to factor, right? Sometimes this is more convenient and sometimes this is more convenient to use. But in both cases we get what? We get the slope of the tangent line at given point 3 here. So we can do it this way, and the rest of the procedure is the same, right? Just finding the slope is a different method. All right. Now, those of you who have read ahead of me, you know that, of course, we can find the derivative of x squared, and that's 2x, and substitute 3 in there, that's 6. You don't really have to do the limit to find it. But the point here is not to do that. The point here, you didn't take this course to take derivatives, and nobody in the market will pay you to take derivatives, because you see that technology right there I just showed you. You can take the derivative faster than any human being on this planet. So taking derivative is not the reason you took this course. You took this course to understand what calculus is, how it is applied, and where do these formulas come from, how do they get their structures, the structures, and how we apply them, right? So that's my goal. My goal is not to teach you how to take derivative of functions. That's just a small maybe side thing that is going to happen anyway, right? And it's very easy, by the way. Taking derivative probably is the easiest thing you can do in calculus. All right, so here is estimate of f prime of 3. We could do that, of course, with a calculator. We did that in chapter 2, right? But I'm going to show you the steps, right? It's just basically estimating the limit, right? So estimating f prime of 3 using calculator is just like what we did in chapter 2. You estimate the limit. How do you estimate the limit? Well, they estimate the slope of what? The average rate of the function, which is the slope of the tangent line, slope of the secant line. So what you do, you put the function in a1 and y1, and in y2, you put this structure so you can easily find the slope from a point to another point, right? So we can do this with the calculator, and I showed you here how to do it. And we see the slope of the secant line approaches what? As h approaches 0, the slope of the secant line approaches number 6, you see. So we did that in chapter 2. I don't want to emphasize it, but it's important to understand this because we are going to use it to not only find the slope of the secant line, the slope of the tangent line at 3, but we like to find the slopes of many tangent lines because we like to know the pattern that exists, and we like to know what is the function that gives us the slopes of the tangent lines at any given point we like. So we don't have to go through this limit every time, right? So let's talk about that. So to do that, we can, of course, let's practice a little bit more with this limit, and then we're going to do it with GeoGebra. So let f of x be that, find f prime of 2 using what? Using this structure, just to practice with it. Okay, so here's our function, and the structure says f of x minus f of a. So basically here we have, again, we have 2 points. We're going to name them this way, a and x. So the values, the function values would be f of a and f of x. So the slope of the secant connecting these two would be that, right? Now we let x approach a. And again, don't try to substitute and find the limit because you always fail if you do that, right? Remember, trouble is built into this. And the trouble is 0 over 0. So this, well, again, but by factoring, right? Factor the numerator. If you forgot how to factor, just review it. It's really easy to factor. I think I showed you how to do it in an easy way in videos on chapter 2. But those are the factors of that. And this gets cancelled, so the answer is 8. It's 8. So the slope of the tangent to the graph of this function at 2 is 8. Okay? All right. What about using the other structure? This is another one. This is the same one. Or we can use the other structure. For the other structure, what we have to do is this. We have to call the first one 2, right? And we want to call the other one 2 plus h, right? So that's one way. So this would be f of 2. And that would be f of 2 plus h. And then we set up this slope, right here. And then we let h go to 0. Again, substitution won't work, right? So what do you have to do? You have to simplify it, factor, whatever you have to do to get rid of that h. And once you get rid of that h, when h goes to 0 here, the answer is 8, right? If you want to use the other setup, you have to call this a 2, and you have to call this x. So that would be f of 2, and that would be f of x. And again, you set up that limit right here. You substitute what we have, and then do it by factoring. All right? So one application of calculus is application of calculus to rectilinear rectilinear motion when an object is moving on a straight line. Okay? So in general, if we have the position function of an object moving, then position function s of t gives us the position at different t values. Let's say we are from t value a to t value t, right? So if this is the position function, then what would the slope of the secant line and tangent line represent in this case? Well, we know that delta y here, or delta s is the difference in position, and delta t is the difference in time. And you know, difference in position over difference in time is actually velocity, right? So that would be average velocity, and ds over dt, or s prime at t, is velocity at t. So that's the velocity, and that's the position. Okay? So instantaneous velocity at time a is the derivative of the position function at time a. So v of a, which is velocity, instantaneous velocity, not average. Average velocity would be the slope of the secant. But this right here is the slope of the tangent at a, right? And that's that limit, of course. Now, instantaneous rate of change of temperature at time ta is the derivative of the temperature function. So if you're given a function that gives the temperature at any given time of the day, for example, then the derivative of that gives us the instantaneous rate of change. For example, at 12 p.m., how fast the temperature is increasing. That would be T prime at 12 p.m., right? But you can say, what's the average temperature increase from, let's say, 10 a.m. to 12 p.m., right? In 2 hours. That would be the average rate of temperature changing. But if you want to know how is the temperature increasing or changing at 12, that would be the instantaneous rate of change of temperature. Instantaneous rate of change of profit at x equals to a. So if P of x gives the profit of selling X number of products, then P of X gives the profit at any given number of products sold. So P prime would be the rate of making profit at the level of this many products sold. So let's say if you're selling 1,000 products, at that level, what is the rate of profit? Increasing or sometimes decreasing. And so these are some applications of this idea of instantaneous rate. All right, now we want to talk about derivative as a function. Derivative as a function. So here, again, we can use this, right? At any given function, you can use this limit to find the rate at this point, or at this point, or at this point, right? At any given point, we can do a limit. But that's cumbersome and maybe not necessary. So how do we get around that tedious work? Well, we are going to see if there is a pattern. So let's look at a function and then find all the slopes and then graph these and see if there is a function actually that gives us the slopes without really going through this limit business here, right? So to do that, instead of calling this first point A, I'm going to just call it X. And we're going to call the next point X plus H. So our slope of the secant will look like this, and the limit of it. So a function is said to be differentiable at a if f prime at a exists, right? If f prime at a exists, then we say that a function is what? Differentiable at a. More generally, a function is said to be differentiable on S, which is an interval, if it is differentiable at every point in that open interval, right? And is a differentiable function is one in which f prime of x exists on its domain. So that means this limit exists in the domain, the whole domain of the function. If that's the case, we call the function differentiable. So when we say a function is differentiable at a point, it means this limit exists at that point. If we say that a function is differentiable, then that means that function is differentiable at every given point in the domain. All right. So again, we can do that with the calculator. We can take a function, let's say x to the third power, and then create a table of values of x, let's say 1 through 7. We go to 7 as well, but we're not going to use the last one because we are interested in the rate between 2 points, right? So how do we find the rate of change from 1 to 2? Well, we have to go to f of 2, right, minus f of 1, and then divided by 2 minus 1, right? That's the rate from 1 to 2. How do you find it from 2 to 3? It would be f of 3 minus f of 2 over 3 minus 2, and so forth. We can automate this process using calculator or a computer program. So to use a calculator to automate this, we can do this. Let's do it quickly together, and you can actually do this by yourself, maybe. So let me first go put x to the third in y1. Then in y2, what I'm going to do is this. So I'm going to put this in y1. I'm not going to use y2 actually. I'm going to go to right here. I'm going to go to stat. And in fact, I'm going to turn this off so don't even get graphed, right? And then what I'm going to do, I'm going to go to stat, edit, and then clear L1 and L2. So I go to the name of the title and press clear, enter. Then go to the name of the title and press clear, enter. Then in L1, I'm just going to put my numbers 1, 2, 3, 4, 5, 6. And I'm going to put, yeah, that's good enough. So in L2, what I'm going to do is this. I'm going to go to L2, the title. If you use Excel program, you know that in Excel you can put a formula in a cell. This is similar to that. So what I'm going to do, I'm going to put this formula here. I'm going to put this formula in L2. So what the formula does for me is it takes L1, which is this number. Let's say over here in this cell, it takes this number, substitutes that plus 1 in the function, right? So basically, remember to find the rate between 1 and 2, right? I have to do f of 2 minus f of 1 over 2 minus 1, right? But f of 2 means what? Means y1 of 1 plus 1, right? So that's the idea. And 1 is in L1. And then f of 1 is just y1 of 1, right? And 2 is really L1 plus 1. And then this 1 comes from L1 again. So basically that's what you get. So you automate it this way. So I'm going to do that. So I'm going to put parentheses. I'm going to go get y1. Remember, y1 is under variables. We talked about that in the previous videos. But it's under variables, y variables and function. So you get y1. And then you put L1, which is right here. I have to put parentheses first. parentheses, and then L1 plus 1, and then minus, I go get y1 again, and then again parentheses, L1, and parentheses close twice, and then divided by, and then parentheses again, I put L1 plus 1. Now, of course, in this case, I could just put 1, right? Because that's what I'm going to get. But the reason that this is the same is because I decided to go with 1 unit. But in general, if you don't go by 1 unit, just put the formula in there. So, and minus L1, so which is basically 1, right? All right, so here you go. There. So you see, these numbers are actually what? These numbers are like 7 is the rate from 1 to 2. 19 is the rate from 2 to 3. 37 is the rate from 3 to 4, and so forth. So what I'm going to do now, I'm going to graph these like points that you see over here and see if there is a pattern here. And we're going to see that this pattern actually is the derivative function. So let me do that. So what I'm going to do, I'm going to go to stat, not the stat, but second, stat plot. Then I'm going to pick the first one, turn it on, press enter to turn it on. Then I'm going to go to scatter plot right here, L1 versus L2, and then I'm going to go to zoom 9. There, you see? Now here is something interesting. Now I know the derivative. The derivative function is 3, and we're going to learn that very soon, is 3x squared. That's the actual derivative. So let me graph it. And as you see, we came close to the derivative. So these points are close to what we are supposed to have, which is basically this graph. Now, why don't we have that is because we are not, remember, we are not close enough to what, when we take the limit, we are not close enough. We have to take the limit to be close enough. This is not really good precision, the ones that we found, right? So in order to be close to the derivative, we have to increase the closeness of these points. So we have to go to like 2 points really close to each other, right? In order to be able to find that function that is the one the calculator has. Okay, so let's. So that is the derivative function. So what I'm going to do, I'm going to show you how this is done by computer. So computer, the GeoGebra, we can automate this. And right here, remember how long it took us to do it for like only 6 points? Now the calculator does it for many, many points automatically. And it gives you, so let me zoom in a little bit here. All right, there. So you see that little red point right there? That is the derivative, that is actually the slope of the secant line when I am this close to this point, right? So that's the slope of the secant from point 1.19 to 1.29 because my h is 0.1. And notice when I move this green dot, and this the notes, when you go through the PowerPoint notes from the Google Doc that I have, you can actually click on this and play with it yourself. But you see, I'm going to move this, and for every point that I move, computer quickly calculates what the slope of the secant, right? For every point, it goes 0.1 to the right of it and finds the slope of the secant. And it gives me those red points, you see? I'm going over this function, and you see how the slopes actually create that function. You know what that function is? That function is derivative of this green one. Okay, that's the idea of derivative. So now notice that you just zoom in and out to get rid of all the red points. If I make h small, I mean bigger, let's say for example, let's make h 1, right? If I make it 1, then let me make it something a little bit bigger. Let's say 0.9. There you go. Let me reload this so I can clear that. All right, so if I can make this maybe 0.6. There you go. 0.6. Now if I move this, you see it's missing. So the precision went down. It's supposed to hit the blue graph, and look at where it's hitting. It's hitting way outside of it. So if you're far from the point, you don't get good precision. So your h has to be really, really small. And that's the idea of infinitesimal, right? All right, so let me close this and go back here. And so let's talk about two interpretations of derivative of a function at a given point. You can think of it as the slope. We can think of it as the slope of the tangent line to the graph of the function. So you can think of a function, let's say this is the function and here's the point. So when we talk about derivative of a function at that point, one interpretation is the slope of that tangent line at this point, right? That's one interpretation of derivative. Another interpretation is the rate of change of the function with respect to the independent variable x at a given x value. So another interpretation is like, for example, let's say this function is increasing. So how fast is the function increasing at that point? Right? What's the rate, instantaneous rate of this function increasing at a? And that's another interpretation of derivative of a function. Okay? And this process is called taking derivative of a function, right? So to find the derivative, we change our naming procedure of the points that the secant line goes through. So the naming procedure would be x and x plus h now. And then in this process, when we find a limit at x, instead of ending up with a number, right, we end up with a function in terms of x, right? In terms of x. Of course, if your function is a linear and you take the limit of it, you're going to end up with a number. But in general, you end up with an expression in terms of x, and that would be your f prime of x, which is the function that we're looking for. And if somebody says, if we have f prime, then if somebody wants to find the slope at this point, right, then we just substitute that point in f prime and we have it. All right, so find f prime of x. Well, we're going to apply the limit, right? And which one is more convenient? You're going to learn by practicing that which one of the structures is more convenient to use. Here we use x plus h. So we're going to substitute in this difference quotient, right? And you go through, you can stop the video, go through this, make sure you see the algebra, and we end up with an expression. We could get the h out of it and cancel the h's, and we have a limit. So what is that? Well, that is derivative function. So that means if somebody says how fast this function is changing at x equal to 3, just substitute 3 here, right? Once we have a function for it, then we have the derivative at any given point, right? And in this case, it turns out to be negative 6x minus 5. And you see the graph of the derivative. This is the graph of the function, and the blue one is the graph of its derivative, right? And you can tell. How can you tell? Now look, what's the derivative of the function at that point? Well, obviously at that point, the slope of the tangent line is 0, right? So the derivative at this point should be 0, and it is, you see. That's f prime at that point is 0. What's the derivative, let's say, at this point, right here? Well, let's see, the slope of the tangent line at this point, it looks like a negative number. What negative number? That right there, that. So the slope of that tangent line at that point is about negative 2.5. So you see? All right. So what's that? Well, again, we can set up the limit again. And you can, again, stop the video and go through the procedure. These are stuff we did in chapter 2. How do you find the limit? Well, you can't do it with substitution. As I said before, the trouble is built into this, so you cannot do it by substitution. So what do? You use the methods we used in chapter 2. You multiply by conjugate. You have a minus b multiplied by a plus b over a plus b. And then the square roots go away. Don't multiply in the denominator because we are hoping to get cancel h. So simplify the numerator, and then mysteriously somehow, well, mathematically, we get something we can cancel h. And we get that. So that is the derivative of square root of x. You can memorize maybe derivative of a square root of something is 1 over 2 square root of something. All right? Well, we talk about these later. But look at the graph. Again, what is the slope of the tangent at this point? Well, we can easily find it. It is right there. It is 1 point something, right? What's the slope of the tangent at that point? Well, we can find it. It is right there. It's like 0.7 something. That makes sense? And so forth. All right. What is the slope at this point? Well, is not defined because it's a vertical line, right? So the denominator goes to 0 here. So the slope at that point does not exist. That means this function is not differentiable at 0. Square root of x is not differentiable at 0, even though it is defined at 0. F of 0 is 0, but is not differentiable at 0. That means the slope of the tangent line is not a number, right? All right, notation to express the derivative. We use a variety of different notations to express the derivative of a function. Now, as I said before, delta y over delta x is used for slope of the secant. So if you can take the limit of this when delta x goes to 0, we end up with dy dx, which is the same as derivative at x. This notation is called Leibniz notation. So Leibniz notation, instead of using F, this is Newton's notation, and this is Leibniz notation. Leibniz notation is it turns out to be much more useful in differential equations and in other math courses. But we can use both in this course. So dy dx means derivative of y, the function y, with respect to this variable x, right? And we can also use y prime equals to. So if you could think of f of x as y, you can think of its derivative as y prime. And we could use d f dx So instead of y, we can just use f. Or we can use d over dx of f of x. So we can think of this as an operator that operates on what? On a function. And the operation gives you the derivative of that function, of course. So d over dx of x squared is 2x. Okay? Now, what about the values? What if you want the derivative at a given point? Well, if you have this notation, you just substitute for x. And the notation is this right here. If you use y prime notation, you can just do y prime of 3. If you use this notation, usually the textbooks have this notation here. So we put dy dx with a little segment, vertical segment, and we put x equal to 3 here. That means substitute 3 in here to get the answer. Again, for df dx, we do the same thing. For d over dx of f of x, we could do the same thing. You just put f of whatever that number is. All right, so you have to be familiar with all of these different notations. All right, so dy dx notation, called Leibniz notation, is quite common in engineering and physics. So in delta y is the difference in y values. We talked about that already. Remember, there was a mistake on that page I fixed. So you see dy is that right there, and this is dx. Delta x. This is delta y, this is delta x. Delta x and dx are the same. But delta y and dy are not the same. You see, if I draw the tangent at this point, right, then that distance right here is our dy. See, that distance is dy. But that distance is delta y. So when we take the limit of delta y over delta x, we get dy over dx, and that's the Leibniz notation. That basically means the slope of the tangent, you see, rise over run, dy over dx. Okay? And then, so we know that delta x here is x plus h minus x. So it's h or dx, the same thing. And f of x plus h is f of x plus delta x. So you can think of this as, h is the same as delta x, right? The same as dx. All of those are the same. But we use delta x because dx has a meaning that we actually did the limit and we got this out of the limit. So here we haven't done the limit here, so we're not going to put dx, we're going to put delta x. So f of x plus h minus f of x, the difference between the two y values, is delta y. So if you isolate this, we see that f of x plus h equals to f of x plus dy, right? So that's the idea. All right. Now there is a really interesting video here at this link, and when you read the notes, you can watch it. It's like 30 minutes, 20 minutes maybe. And this guy talks about this idea that the instantaneous rate of change is actually an oxymoron. You can't have instantaneous and rate together, and he talks about how calculus actually resolved that. And we talked about it already, but that's a good video to watch. All right, identify the graphs of f of x and f prime here. Which one is f of x, which one is f prime? Well, think about it. We talked about this already. If you go to any point, let's say at this point, when you draw a tangent at this graph, the other graph has to give you the slope value. We know the slope value here is like some positive number, right? It's not 1, it's less than 1, and you see this graph gives you that, right? So it looks like the blue one is the graph of the red one. It cannot be the other way around. It cannot be the other way around. Why? Because let's say, what's the slope of that line is a negative number, but the red one doesn't give you a negative number, right? So the red one cannot be the derivative of the blue one. The blue one is the derivative of the red one. Or the purple one is the derivative of the red one. Okay? What about this one? Well, you do the same thing, right? The best point is like here. What's the slope of that tangent line? Is 0, and looks like the purple one gives you that. So the purple is the derivative of the red, right? All right, so what about here? Well, don't say purple is a derivative of the red, because I switched the colors. So what about here? So what's the slope of the tangent line at that point? Well, it's supposed to be 0, and looks like the red one gives us that. So in this case, the red one is the derivative of the blue one, right? Can't be the other way around. All right. And what about this one? Again, the trick is to go to one of them, let's say this one, and draw a tangent at that point. What's the slope of that tangent? It's 0, and looks like the red one gives us that. So the red one is the derivative of the blue one. I think I gave you the other way around. So let me just go to 2 points, because it could be misleading. So let me go to that point. And what about this point right here? Let's say this point. Well, the slope of that is negative, and the red one is positive, so it doesn't work, right? So I should have checked more than 1 point to make sure. So it's the other way around in this case. I only checked 1 point. That was just coincidentally it worked, but it doesn't work in the other points, right? So in the other points, any if you put any, try it at several different points to make sure we get the answer, right? So at this point, the slope of that should be some positive number, and it is. Slope here should be 0, and it is. The slope here should be negative, and it is. But if you do that for the blue one, it's not going to work. All right. So now here is, click on the image and change the function. So then compare the graphs of f of x and f prime. So let's do that. So you can come up with any function. It gives you the derivative, and you compare the derivative of the function and the function itself. Right now, we don't know how to find derivative of these functions, but we will very soon. So for example, if I make it x squared, right, that's the graph of the function, and that is the derivative of it. Let's go to something else. Let's say x to the third power plus 2x minus 1. There. Right, that's the function. The red one is the derivative of it. So you can practice with this and compare the derivatives and see if this actually makes sense to you. All right, differentiability implies continuity. It means that if a function is differentiable at a point, it must be continuous at that point. Remember, we talked about continuity. So continuity was basically if a function is continuous at point A, then the limit of f of x when x approaches A is what is f of A. And if a function is differentiable at a point, that means the limit of f of x minus f of A over x minus A when x approaches A is a number. That means it exists, right? So what we are saying is this. If this is true, then this has to be true. If the left side is true, then this has to be true. That's what we are saying. Not the other way around. So let's see if we can make sense of this. Can we prove it actually? And the answer is yes. Here we go. So the proof of it is this. We should assume that this is true, and we have to get this idea that the limit of f of x when x approaches A is f of A. So for the proof, we start from left side and see if we can get this out of it. So let's start from left side. Now, To go in that direction, we can add and subtract f of a to f of x. That doesn't change the value of it, right? But it changes the structure. So let's subtract f of a and add f of a to it. And then we're going to get divide by x minus a and multiply by x minus a over here. This part of it, we multiply it by x minus a and divide it by x minus a. We don't change anything because that over that is 1. And then we keep that as f of a. Now why do we do that? Because now we can separate these two limits. Limit of this and limit of that plus limit of f of a, right? And remember we said that this, we assume this exists, right? And that would be f prime of a. Limit of this when x approaches a is 0, right? And limit of f of a when x approaches a, f of a doesn't care about x because it has no x in it, so it's just f of a. 0 times that plus f of a is f of a. So we got the right side. That means if you assume that this is true, then this has to be true. That means differentiability implies continuity. All right? So does continuity imply differentiability? Not necessarily. And we prove that by looking at some examples. So here's an example. We know that absolute value of x is continuous, right, at 0. So it looks like that, right? It is continuous at 0. Right? It's a V kind of shape, remember? So it is continuous at 0, obviously. But it turns out that it's not differentiable at 0. Why? Because the limit doesn't exist. If you consider that to be 0 and go to another point and call it x and set up your limit, you see that this limit turns out to be this. And we know from chapter 2 that this limit doesn't exist because to the right and to the left we don't get the same limit. Limit from the right, absolute value of x would be just x from the right because you have positive numbers. And so we get x over x, which is just 1. And then from left, it would be negative x. So that would be negative 1. So they're not the same. So that means this limit does not exist. So if the limit does not exist, what does that tell you? Well, if the limit doesn't exist, then that tells you that tells us that that the limit, that the derivative does not exist, right? So what does that mean? That means this function is not differentiable. But remember, it is continuous at 0. So what does that mean? That means continuity does not imply differentiability. With this one example is good enough to refute that idea. But we're going to look at more examples, okay? So now we learn that if a graph has a sharp corner, right? This is a sharp corner. We could also have a graph that has a cusp like that. That's a cusp. So at sharp corners and cusp, derivative does not exist. From the graph of a function, we can tell we have points where the derivative does not exist. Here's another situation, cube root of x, which looks like cube root of x looks like this, right? It kind of goes that way, and then kind of that way. That's cube root of x. So it looks like that at 0, it is continuous, but it's not derivative. It's not differentiable, so derivative does not exist. So what's the derivative at 0? Well, we use the same setup. Consider that to be 0. We go to the point like x there, draw the secant line, and then take the limit, right? You end up with that. That's x to 1/3 over x to first power, which is x to negative 2/3 power, right? That means it goes in the denominator. And then when x approaches 0, this right here goes to infinity. So that means it doesn't have derivative. When the limit for derivative goes to infinity, that means the tangent line is vertical. So if you go try to tangent at 0 to this graph, you get a vertical line, and a vertical line, you remember in math, we don't have what? We don't have slope for it. Even in algebra, we don't define a slope for a vertical line, right? So let's so the limit does not exist, goes to infinity. That means this function is not differentiable at 0, but it is continuous. So that's another example to refute the idea that continuity implies differentiability. It doesn't. So if a function is continuous, we can't say for sure that it's differentiable. But if it's differentiable, we can say for sure it is continuous at that point, right? And that's the graph of it, a better picture of that function, and you see we have a vertical tangent. So that's another place in graphs that you can tell the graph doesn't have derivative at that point, when we have vertical tangent. All right, for the graphs below, determine for which values of x the function is continuous but not differentiable. Well, do we see any values in this graph where the function is continuous but not derivative, not differentiable? I don't see anything on this one, right? At this point, it's not continuous. At these points, it continues, but it's also differentiable, right? What about this one? Yes, on this one, we don't have any. But on this one, yes, we do. At 2, right? At 2. Now, here, at 1 here, right? This sharp corner doesn't exist, right? It's not part of the graph because the graph is defined over there, right? So we have at 1 and at 2, but not because of they have a sharp corner. This is discontinuous already at that point, so we don't care about that point. We are talking about points where the function is continuous but is not differentiable, right? So that's why we don't consider that. Obviously, it's not differentiable at that point either, but it's not continuous either, right? So we're talking about just one point here in this graph. All right, so I'm going to do this example in the next video. This is, and I'm going to end this video. I don't want it to be too long, so I'm going to get out of this and let me keep them so I can see, I can correct the mistake. So I'm going to continue with the next video on chapter 3. I want to say bye to you and take care of yourself and others. I see you in the next video.